Welcome to a video on section 2.5 for pre-calculus, and we're looking at complex zeros and fundamental theorem of algebra. Alright, so we're looking at some notes that you can find in the pre-calculus documents folder, and it's just called 2.5 notes. You can go ahead and print those out, and these are going in your notebook. I believe in 60 and 61. I'm going to have to check on those pages, but I'll definitely put the correct pages in the checklist. Okay? All right. So the fundamental theorem of algebra, let's start there. So the fundamental theorem of algebra is tied to something we've already talked about, and then it has to do with the degree of the function. Okay, so if you have a polynomial function that has a degree of n, then we have n complex zeros. Now we've already talked about how the number of zeros is at most n, but that was when we were talking about real numbers. So now we're saying if we're looking at complex zeros, now complex zeros include basically every number, including real and non-real numbers. So just a reminder of the set of numbers. Let's say we have, this is all the real numbers right here. So that includes things like natural numbers, integers, and rational and irrational. So we'll say irrational is in here. All of this is real. But then we also have the imaginary numbers. So we'll call this imaginary. So when we talk about complex numbers, what we're talking about is both of these put together. So complex numbers are anything that can be written in the form a plus bi. Now we know that I is the imaginary unit, so for it to be in the imaginary section, b cannot be 0. It has to b has to exist. It has to be a number that's, in fact, a and b are real numbers. So a and b are elements of the real number set. So if b is not equal to 0, you're going to end up with an imaginary number. If b is equal to 0, then all you have is an a, because this term will cancel, and so these are also going to be considered complex. Okay, anyways, so if it's a real 0, we'll see it because that will be an x-intercept. If it is a non-real 0, it is not an x-intercept. We can't see things that are imaginary graphed on the x-axis, for example. Okay, now this does include that zeros can be repeated, so remember multiplicity. Okay, moving on, we have the linear factorization theorem, which says if f of x is a polynomial function of a degree that is n, which is greater than 0, so at least 1, and remember that the degrees have to be positive integers, then f of x has precisely n linear factors. Now remember those zeros can be complex, so or they will be complex, which means they can be real and non-real. So how it's written, you have a, which is your leading coefficient, and then you have x minus z1. z1 is your first zero, x minus z2, that's your second zero, etc., all the way through zn. And they're complex, which means they could be real or they are not real. And they don't have to be different numbers. That's what it says by are not necessarily distinct numbers. Some may be repeated. So for example, you could have a leading coefficient of 5, and then your zeros are x minus 1. So 1 would be a 0. And then maybe x plus 2. So that means negative 2 would be a 0. But then you can also have like x plus I and x minus I. Okay? Speaking of imaginary zeros, that leads us to our next theorem here, which says, which is called the complex conjugate zeros theorem. It says, suppose f of x is a polynomial function with real coefficients. That's an important part of this. The coefficients have to be real for this to work. If a and b are real numbers, with b not being 0, then a plus bi, and a plus bi is a 0 of the function. So then its complex conjugate, a minus bi, is also a 0. So what that's telling you is, let's say you have 3 minus 2, or we'll make it plus 2i is a 0 of a function. So it can never be alone. It has to come in a pair with its complex conjugate. So that's where we change the sign in the middle. So if this is a 0, then that implies that the complex conjugate, oops, let me erase that, 3 minus 2i is going to be a 0. So 3 minus 2i is going to be a 0. They have to go together. So let's look at this example here. It says, write a polynomial function of minimum degree, so don't make it bigger than necessary, in standard form with real coefficients whose zeros include -2, 1, and 3 plus I. So the first thing you should notice here is you have this, 3 plus I. And so that means, by this theorem, that its conjugate is also a 0. It has to be a 0. So if you see 3 plus I, 3 minus I has to be included. They're not listing it, but it's there. Okay, so then now we're going to use the linear factorization theorem so that we can write it in standard form. So here's our function, f of x, we'll call it. So this is like z1, z2, z3, and z4. So let's do x minus -2 would be plus 2 times x minus 1 times x minus, now be careful here, I'm going to use brackets right here, 3 plus I. I'm going to use brackets because we're already using parentheses. Now if you don't put some kind of grouping symbols here, that negative sign will not distribute correctly. And then it times x minus, then the conjugate, 3 minus I. Okay, now I don't know what a leading coefficient is. They just, that's not important. So by minimum degree, they're saying don't add any more unnecessary zeros, like a multiplicity or something. These are the zeros. If I wanted to make the degree higher, I'd have to add maybe another x plus 2, or I square it or something, okay? So it wants it in standard form, which means we're going to have to multiply this out. So when you have 4 things like this, 2 of them having complex conjugates in them, you're going to want to do 2 FOIL problems, okay? You're going to want to FOIL these two. That's easy. That's x squared plus x minus 2. Okay, that's this one, these two multiplied. Now these two multiplied, you're not going to want to distribute these negatives. I think it's going to be easier if you leave them like that. Okay, so we're going to carefully FOIL these things, okay? Okay, so let's do x times x. That's easy. That's x squared. Remember that we're going to multiply this, so I'm going to keep this all in parentheses. And then you're going to have a negative bracket 3 minus I x. And then we're going to, so I multiplied x times this whole thing. I can distribute it later if I want to. Okay. Then I'm going to do an x times a negative, so another minus, a 3 plus I bracket x. And then we're going to do 2 of these two brackets together. So a negative times a negative on the outside will give you a positive. Okay. And then off to the side here, I'm going to multiply 3 plus I times 3 minus I. Now you may remember when you multiply complex conjugates together, it actually turns out to be nice. It's actually just a number. The i's will cancel, so that's a 9. You're going to get a 3i and you're going to get a negative 3i, and those are going to cancel. Alright, you don't have to write this, but I'm just going to show you. You get a 3i and a negative 3i, those cancel. And then you get a negative I squared. Now remember, I squared is negative 1. So this is a negative negative 1. So altogether this gives us 10. So I'm going to put that right there. Okay. So then now let's clean this up. We can, in fact, you can think of it, there's a negative that's being distributed and there's an x that's being distributed. So you could do them separately, or I'm going to do them together. So this is x squared minus 3x plus x times I. And then I'm going to distribute the negative here, and I'm going to distribute the x here. And that's going to give you a negative 3x minus xi plus the 10. What should happen when you multiply these complex conjugate zeros together is the i's will cancel out. You're not going to have any i's left over when you're done with this process, I promise you. Okay, because it has to have real coefficients, and if there's any i's left over as coefficients, you did something wrong. So you see that positive xi here and the negative xi here are going to cancel. I apologize that I probably didn't give you quite enough room to complete this, but we're almost done, but it might be a little tight here. Okay, so let's see what we have so far here. We have x squared plus x minus 2 in one parentheses times, we have an x squared minus 6x plus 10 in the other one. Okay, now we have to multiply these two trinomials together. Just one step at a time. I'm going to first distribute to the x squared. We get x to the 4th minus 6x cubed plus 10x squared. Okay, next I'm going to distribute the x to everybody. Think of this as just 3 distribution problems. And when I distribute the x, I'm going to put like terms underneath each other. So x times x squared is an x cubed, so I'm going to put it under this x cubed. X times a negative 6x is going to be a negative 6x squared. And then x times 10 is a 10x, which I don't have any x terms, so I'm just going to add it on. Okay, one more, and then we combine and we're done. Next, I'm going to distribute the negative 2. Negative 2 times x squared is negative 2x squared. Put it under the x squared term. Negative 2 times negative 6x is a positive 12x. And a negative 2 times 10 is a negative 20. Now let's just add up everything. Okay, negative 20, 22x. That's going to be negative a, so 2x squared plus the 22x. We have a negative 5x cubed, and then the x to the 4th, there's only one of them. Whew. Alright, there's your function. That is the simplest function that fits this criteria. Okay, next example here. Find all zeros of this function and write f of x in its linear factorization. Okay, so I'm not expecting you to factor this thing. I'm not even going to make you do the rational zeros test like we learned in the last section, although that is a possibility to at least get some zeros. What I'm going to have you do is use Desmos and graph it. But what you're going to see is you're not going to find all of the zeros. So remember that the degree, which is 5 here, tells you you're going to have five complex zeros. So we're supposed to find all of the zeros, including the ones that are imaginary. And so you're not going to be able to see the imaginary ones on the graph. Okay, so let's look at the graph. So it was, I just typed it in, just make sure I got it right. Yeah. Okay, so you can see there's the function. Okay, now it's supposed to have 5 zeros, but it's only crossing the x-axis 3 times. We have -3, a +1, and a +2. So the other two zeros are going to be imaginary. Okay, so we're going to use that to get some more information here. So let's write down those zeros. We know that this is the real zeros. The real zeros are -3, 1, and 2. So what we're going to do is we're going to divide using synthetic division those zeros and see what we have left over. Okay, so for example, I'm going to do synthetic division with -3. Remember, don't change the sign. That is the zero. These are the zeros. Okay, my coefficients are 1, -3, 6, -28, 24. Actually, I have a 0 in here because there's no fourth term. So let's see if I can squeeze a 0, the number 0 in there for the coefficient of the fourth term, right? There's no fourth power. So 1, 0, and -3. Okay. So bring it down, multiply, add, multiply, add, multiply, add, multiply. That's -19. Uh-oh. I did something wrong. Let's see. Hold on. Oh, I see my mistake. I just added correctly. I knew it was something was wrong because I was not getting a remainder of 0. And if this was truly a 0, the remainder needs to be 0. Okay, I just added wrong there. That's a 6. So that's a -18. That's a -12. That is a 36. That is an 8. There we go. And now I'm going to get my remainder of 0. So this stuff that's left over here, okay, so this is a 8, a -12x. This is 6x squared, -3x cubed, and an x to the 4th. Okay. Now I know 2 more zeros. So I can just I could divide this by one of them. Think of it as I'm dividing the function. I divided the function by essentially x plus 3. That is one of its linear factors. X plus 3 times this gives me that original function. So let's think of it as like I'm factoring. I'm breaking it down. Okay. So now I'm going to do synthetic division with this new thing right here as my new coefficients here. So that would be 1, -3, 6, -12, and 8. And now I'm going to use one of the other zeros, like 1. Let's use 1. That's one of the other zeros I know. Let's bring it down, multiply, add, multiply, add, multiply, add, multiply. Okay. Again, if you might want to have some more paper on this, I apologize for not really leaving you guys enough room here. Okay, so let's just keep track of what we have here. So we factored out the x plus 3, and we got this thing. So now what I just did was I essentially factored out the x minus 1, because that's what the 1 comes from. And what you're left with is this stuff. Okay, we should have, so this is a -8, this is a 4x, a 4x squared, and a 1x cubed. Okay, now I could do that one more time, and I could use the 2 to factor, because I know there's still an x plus or x minus 2, and it's got to be in here. Or, actually, this one I recognize as factoring by grouping. I know how to factor this one. So I could use synthetic division and do the same process again, but if you recognize the factoring, you can factor it. I don't know if you guys remember factoring by grouping. You pull out a GCF out of a pair. So the first pair here, I can take out an x squared, and then I can see in the second pair we can take out a 4. And then you have the same binomial here, which is like a GCF, and you pull it out. So there's your x minus 2, and then what remains is an x squared plus 4. So using the 3 zeros that I found originally using Desmos in the graph, I get these 3 linear factors. Now this is a quadratic factor, and this quadratic factor does not factor any further. But we know how to solve this. If we imagine it's equal to 0, you're going to get 2 answers. If you set this equal to 0, you're going to get subtract 4, x squared is equal to negative 4, square root, square root of plus or minus, right? That's plus or minus 2i. And that is your other 2 zeros. So remember, this was a 5th degree polynomial, so the degree is 5, so it has to be 5 zeros. So if we write it as its complete linear factorization, so I'm going to erase some of this stuff. If we write it as the final answer, here's what we get. We had x plus 3 times x minus 1 times x minus 2. These were the real zeros. Then we have 2 unreal zeros. You have x plus 2i and x minus 2i. This and this is your pair of complex conjugates. There's 1 plus 1 and 1 minus 1. They always have to come in a pair like that according to that theorem, the complex conjugates. Okay? And that is your answer to that question. Okay, now just one more example here. This one is actually 100% factorable. I don't know if you remember, if you have something of a quadratic form. So what I mean by that is I have an x to the 4th and an x squared. So I can write this as something squared plus 13 times that same something plus 36. The thing that's being squared here is an x squared. Okay, so when you factor it, you can factor it like a diamond problem. You can go, okay, give me 2 numbers that multiply to make 36 and add to make 13. And that would be 9 and 4. But instead of putting an x plus 9 times an x plus 4, you do an x squared. So you could check this. This FOILs out correctly. X squared times x squared will give you x to the 4th. And then you get a 9x squared here. And then you get a 4x squared here. And then you get the 36. And the 9x squared and the 4x squared will add to give you the 13x squared. Okay, but checking aside, we are looking for the zeros of this function. This is not factorable, this is not factorable. In fact, we just did this one. You're going to get plus or minus 2i. X squared plus 9, you're going to subtract 9 from both sides, right? Set it equal to 0, subtract 9 from both sides. You get x squared minus 9, square root, square root. You're going to get a plus or minus 3i. So the degree is 4. All 4 of the zeros are imaginary, and they go in pairs. They have to go in pairs like that. Okay. I was going to show you the graph of this one, because this one does not cross the x-axis at all. So I'll make this one go away. It kind of looks like a parabola. It's a fourth power though, so it's a bit skinnier. But it doesn't cross the x-axis at all. All of its zeros are imaginary. Okay. So now let's talk about something called irreducible over the reals. So we say a function is irreducible over the reals. What that means is, let me erase a little bit more here. What that means is there are no real zeros, and what you get is the factorization. When we factor it, so the factorization has no linear factors, but it has irreducible quadratic factors. So irreducible quadratic factors are like these things: x squared plus 9 and x squared plus 4, because you can't factor those at all. You can kind of solve them using like square roots, but they're not factorable, so we say they're irreducible quadratic factors. Okay, so this is an example of a function that's irreducible over the reals. There's no real results, okay? All right, factors of a polynomial with real coefficients. So every polynomial function with real coefficients, that's important that they're real, can be written as a product of linear factors and irreducible quadratic factors. Okay, so they can all be broken down to either all linear factors or irreducible quadratic factors. So we're going to do this example. We're going to write x to the fifth minus x to the fourth, that big function there, as a product of linear and irreducible quadratic factors, each with real coefficients. Okay, so to get the zeros to begin with, we can use the rational zeros theorem, or the rational roots theorem, either one, to use the factors of 3 and the factors of 1. And since that's a small list, like the factors of 3 are 1 and 3, right? So you're going to have plus or minus 1 and plus or minus 3. And the leading coefficient is 1, so you're just going to divide those by 1. So that's 4 possible rational zeros. That's it. That's a tiny list. So that is an easy one to start with. So on synthetic division, if we plug in the number 1, we get a remainder of 0. So let's look at what we have remaining here. This is negative 3. This is our remainder. We don't have any x terms, but we have negative 2x squared. We have no x cubes, but we have an x to the fourth. So I showed you an example earlier where you have quadratic form. Okay, you have this term x squared, and this is that term squared. That's x squared squared. So it follows the pattern of a diamond problem. Two numbers that multiply to make negative 3 and add to make negative 2 are negative 3 and 1. So you're going to do minus 3 and minus 1, but you're going to have x squared here. Except this is a positive 1 right here. Okay. So then in the front here we also have the one that we divided by. That's the 0 from x minus 1. So then this, you're going to get, if you set that equal to 0 and solve that, you're going to get the zeros of plus or minus the square root of 3. Now these are not imaginary, they're radicals, and in fact, I'm not sure if where this theorem is. I don't know if we skipped it, but just like the complex numbers that come in pairs of conjugates, irrational numbers come in pairs of conjugates. So you're always going to have a plus one and a plus and a minus. So we can break this up into x plus the square root of 3, x minus the square root of 3. They're not rational, which is why they weren't in our rational list. And then this one, x squared plus 1, if we solve that, that's where we get imaginaries, because we're going to have to subtract 1. In fact, we're going to get, well, we would get x plus I, x minus I. But remember the question said, write it as a product of linear and irreducible quadratic factors. These are all linear. This is a irreducible quadratic factor right there. Okay, because it's going to give you not real stuff. Okay. All right, I think that's it. Actually, I just want to show you the graph of this one. Let's turn off the blue one. So this is what the graph of that one is. So actually, I think I typed it in wrong. X to the 5th minus x to the 4th. Yeah, okay. I forgot a term here. That's why it's not matching up. Plus 2x squared. There we go. So there is our rational 0 of 1. 1.732, that is the square root of 3. And there is the negative square root of 3. So those are real numbers, and so you get x-intercepts along all those numbers. The other zeros are imaginary, so they are not x-intercepts.